excellent to be back in my original hometown of London at PyData in person again. I do have too much material, but we're going to turn that into a virtue and turn various things into exercises. I didn't know I was going to have too much material till I tried doing it. So I'm sorry about that. I'm going to try not to waste too much time. We're going to be talking about parallelism, and in particular MPI and MPI4Py today. I think it's a pretty important topic, and even if you don't end up using it, I think it should help you understand what's going on in parallel systems today. Hopefully everyone got the email with the instructions about what you need to install to do the sort of type along stuff here. So you need a working MPI4Py, which means you have to have installed a copy of MPI. If you haven't, you're probably too late. But what we'll do is when we start the well, maybe I'll do a show of hands. Maybe I'll get to a point where I can see people. Who has a working MPI4Py? Right, I was thinking we could like pair up or something like that. So, but it's looking like it might be more. Okay, well, okay, that's well, that'll be interesting when we get to the practical part. Yeah, maybe I'll maybe I'll show you more than we'll do. The trouble is we can't do the installation now because the installation could take anything up to an hour for each person. And if I go around helping people install one at a time and we've got an hour and a half, it's not going to work. If I could do it in parallel and do all of you at the same time, that would work. But given that you don't all have identical systems and identical levels of experience, that's not going to work. Okay, let's not waste more time. We'll get on. Don't worry about it. We will make it work. Yeah?
I got the email. I see that installation instructions recommend like building MPI.
Yep.
I understand
yep.
That's the tricky part.
Yep.
Isn't this available in Conda as a pre-built package?
I don't know. If it is, maybe that will help you. I don't think so, because but I guess it's possible. Okay, let's without too much further ado. So the slides are available from this URL, if people haven't got that, in case anyone can't read it at this scale. They're also available from GitHub. So there's a repo that you should download. You should git clone this thing here, which has the code examples and the slides in it. And that means even if you don't have a working MPI4Py, you can get yourself a working MPI4Py afterwards and try all the examples. I strongly recommend that, well, I was going to strongly recommend that you type the examples because I think you really learn something by typing, but yeah, maybe you'll learn something by typing even if you can't run them if you don't have installations. You should also be familiar with the documentation for MPI4Py, which is the library we're going to use, which is available from that second URL. And MPI4Py has a set of examples with it in the tutorial, and I have reworked a number of those examples and I think made them clearer and better. And you can also clone my enhanced versions, or at least what I claim to be my enhanced versions of those from that second URL. Now, I didn't really think this through because I can't really leave those up and move on to the next bit. Ah, well, yeah. So I will leave that up and just talk a moment. So parallel computing is a huge topic. Parallel computing has existed for, I don't really know how many years, but certainly since I started doing it in the 80s, and I wasn't the first person to do it. So it's at least 40 years old, probably more. And basically, all computers are parallel now. And there are lots of different abstractions and lots of ways of taking advantage of parallel computers. I guess I'm going to hope people have got that. There are lots of words around this that you will have seen. I'm not going to read through them all. And we're not going to cover all of these. The ones you're most likely to hear in Python are the GIL, which should probably be in giant letters because the GIL is the big problem for parallelism in Python. If you use MPI in the way that I'm talking about, the GIL doesn't matter. The GIL is not an issue anymore. We're not going to talk about async IO or async await or any of that sort of stuff. The stuff we're going to concentrate on is the stuff in red, if that looks red from where you are. Yeah, that really didn't work, did it? Well, we're definitely going to concentrate on the dark stuff and the bits that do look a bit redder if you downloaded the PDF. That's all a bit disappointing. Anyway, okay, so what is parallel computing? Sorry, I should say we're going to start. There's going to be about half an hour of chat. I'm going to try very hard not to run longer than that. And then we're going to start doing the exercises, which, okay, might be more me showing you things than you typing if most of you don't have a working MPI, but nevertheless. So parallel computing, well, what is parallel computing? Well, serial computing is, doing things at one time. So it's like one person doing something, and I hope I'm not going to get in trouble for saying it's like a man doing it, a man who can only do one thing at a time rather than a woman who can multitask. But it's doing one thing after the other. There's just one stream of execution, one stream of stuff happening. We know this. This is how we normally think. Now, modern computers aren't like that anyway. The screen's updating at the same time as, and there are multiple chips in your computer, even ignoring the CPUs. But conceptually, that's what the classical conception of serial computing is. And parallel computing is doing several things at the same time, literally having different streams of execution going on. And in particular, to call it parallel computing, we normally mean that those different processors, those different bits of execution are contributing towards the same task. So it's like breaking a problem down, having a team of people, digging a hole or erecting the building rather than a single person building the building, rather than just lots of people all doing their own thing. It's a coordinated activity towards an end. There are other things related to parallel computing, like clustered computing, which is where you have a bunch of machines, each of which may be parallel or which may be serial, and which are connected together maybe by a local area network, or a network in which you might throw jobs at. But that's different from parallel computing, basically because it's not tightly enough coupled. There's also, the thing that really confuses people is concurrency. Concurrency is not, in general, parallelism. Concurrency is the idea of several things being done over the same time period, but only one of them being done at a time. So it's like if you have 4 tasks, it's like you do a bit of task 1, and then you get paused, and then you do a bit of task 2, and then you get paused, and then you do a bit of task 3, and then you get paused. And this is how time-sharing systems have worked forever. Before we had parallel, mainframes and things, we had serial mainframes that had a supervisor script or a supervisor process that said, right, user 1 can have a bit of time now, and then we're going to kick that user 1 out, and we're going to run user 2's bit. So concurrency is not parallelism. Concurrency is about breaking up a problem so that different bits can run sort of independently, but not necessarily at the same time. And in general, with concurrency, not at the same time. So you can have concurrency on a single serial processor. You're thinking about time sharing, you're thinking about interrupts, you're thinking about threads and stuff like that. There are a bunch of different parallel computing architectures that we'll talk through briefly, more briefly than I originally intended, because I produced too much stuff. So we talk about SISD, SIMD, vector processing, and MIMD, and I'll go through those. So SISD, we only talk about SISD because it helps to explain the parallel stuff. So SIMSD, single instruction, single data. That's normal serial sequential execution. For example, testing primes using an ordinary Python program like this that we don't need to go through because you all know how to test primes and you all know how serial computing works. And so that's finding whether 29 is prime, which it turns out it is. So the point about talking about SISD is that there's also SIMD. So SIMD, single instruction, multiple data, and the examples of these that you'll know best are GPUs. GPUs are SIMD systems. And the idea with SIM, and I'm from Edinburgh. I was actually one of the first people employed in fact, the first person employed at the Edinburgh Parallel Computing Centre in 1990. And in Edinburgh, the first parallel machines we had were ICL DAPs, distributed array processors, and we eventually had the sexiest computer that was ever built, the Thinking Machines Connection Machine 200, which had 65,536 bit serial processors, so 1-bit processors. And GPUs are like this today, except they use whole words, not just single bits. And so the idea with SIMD is that you have a single program executing, you have a single instruction pointer, so every process or every processor is doing exactly the same step at the same time, but you have lots of simple processors that all execute that program in lockstep with each other. So think about an image and some image processing task where you need to apply a filter, and you only need maybe the pixel and maybe its immediate neighbors or its second-degree neighbors or whatever, and you can just run over the image, and if you've got 10,000 processors, you can do 10,000 pixels at a time. If you've got 100,000 processors, you can do 100,000 processors, and these days you might have a lot more than that. So that's SIMD. All branches execute on the same data. It means you can't exit early from loops and so on, so if you imagine doing this to test primality, if you find that a number's prime, it doesn't mean you can stop because you still haven't found whether all the other numbers are prime yet, so you can't exit early. You can't take different branches on different things. You can have a mask that says where this is true, do this, but it's not literally only doing one of the things. So this is ideal for things like graphics. It's ideal for lots of physical simulations because physics is local. And so if you can kind of chop up a problem's, space-time or an aircraft wing or something into bits, that can work well on an SIMD computer. But it's relatively inflexible. So I have got little animations here that show, a whole load of inputs, and, suppose we're randomly multiplying them by 2. They all get multiplied by 2, and then we're adding 3 to them. This program is not doing anything useful, but, then we add 3 to them all, and then we go backwards, because I'm not very good with computers. Don't worry about that. And then maybe we have the equivalent of an if statement where we say, where the number's bigger than 10, negate it, otherwise double it, or whatever. And that probably actually happens in 2 separate steps. But the point is, you can have ifs. It's just that you kind of execute both branches everywhere, but only apply the result. And then you cube it, and then you produce all your outputs at the same time, or whatever, right? And so this example here was an example of 8-way parallelism, but think 65,536 or a million or like crazy large numbers of things going on GPUs. Okay, and I've got an example of doing the prime testing here again, but because you can read it through in your leisure if you like, but you can imagine. The point is, all those bits where you say, let's exit early, they don't work, testing primality on an SIMD machine. Okay, vector processing. Vector processing, again, maybe the second sexiest, maybe sexiness isn't the right thing for computers, but anyway, this was a Cray XMP, which was one of the, there was actually a YMP after it that was even better, but they were these amazing looking computers that were vector processed. They were the fastest computers in the world at the time. And again, you have a single process, but you have multiple execution units, and you have a pipeline. And the idea is different bits of the pipeline they might do the same operation, but in general, different bits of the pipeline do different bits of the operation. And you think of it like a conveyor belt. And what happens is you kind of fill up this conveyor belt, and to start with, the conveyor belt's empty. And so at the first cycle, you only process the first bit of data doing the first operation. But at the next unit, so you start off with a sort of queue of inputs like this, and then if we're doing this same stupid operation we had here, at each clock cycle, everything kind of moves left at the top, and so then you multiply the first one by 2, and it produces 2. But now 3's moved into that input area, and so at the next cycle, the 2 moves down and gets a 3 added to it, but the 3 moves down and gets doubled, so we end up with a 6 and a 5. So now we're doing 2 things at the second step, and now the 7 can move in, and at the next step we'll be able to do 3 things because the 5 can get doubled, and the 6 can get 3 added to it, and the 7 can get multiplied by 2, which is a lot like doubling, isn't it? But anyway, and things move down the pipeline, and eventually, when you've filled up the pipeline, now you're doing 4 things at a time, and this pipeline might be a lot longer than 4. So if you've got, you might have a 100-element pipeline or something, and now you've got 100 parallelism. But different things are at different steps, and then you start producing the outputs, and the outputs will. This is vector processing, and at one point this was the fastest kind of computing there was. Okay, but what we're going to be concentrating on today, 15 minutes, not terrible, is MIMD, multiple instruction, multiple data, which is of course the most flexible thing. So multiple again, it's all very Edinburgh focused. So this was the first MIMD computer we had in Edinburgh, which was a Mako computing surface, which was a 40-processor machine. It had 40 transputers in it, and then it gradually grew to about 320. And now the EPCC has a machine with 750,000 full processors in it, which I really struggle to get my head around. And so now you have potentially different, you have a bunch of processors. They're all kind of independent, though they can talk to each other, and you're running potentially different programs on each processor. Now, in fact, most of the time you run the same program on every processor, so-called single program, multiple data, but they all have their own instruction pointers, so they can be doing completely different parts of that program. And indeed, you kind of force stuff into this SPMD for convenience model, but often there are different functions that different processors are doing. But still, the general idea is you've just got a bunch of processors all doing their own thing, but cooperating to solve a problem. And so with MIMD, you can exit early because you can just, you've just got an ordinary computer. Okay, so that's the basic idea of MIMD. It's just a whole bunch of different computers together. And I don't know what laptops we have in the room, but I would be surprised if we have any laptop in the room that doesn't have more than one core, more than one CPU, if you like, in it. Maybe there's a really old one that doesn't, but it's unlikely. So there are 2 different, within MIMD, there are two different architectures, two different main architectures, so-called shared memory and distributed memory. And again, every computer in this room is probably a shared memory computer, but perversely, we're going to use a distributed memory programming model for reasons that, if I do a good job, will become clear. So what's shared memory? Well, shared memory is what it sounds like. If you have, I can move, right? Because I can move. I mean, you can still hear me if I move. I can definitely move. So if you have 4 processors, then you have just one big block of memory, and all the processors can talk to that memory, right? And none of my architecture diagrams are real architecture diagrams. These are conceptual programmers' ideas of what's going on. Don't worry about what's actually going on in the hardware. But maybe they all go through a memory controller, or maybe they all have their own memory controller, or whatever. But the point is, all of them can read and write from any bit of that memory, and all of the bits of that memory are just as fast as any other bits for reading and writing. And so it's dead simple. And what people like about this is it's conceptually very simple. You've just got a whole lot of processors, a big bunch of memory. Anyone can read or write anything. So that's fantastic. The only con is that you have to orchestrate that, so you get contention when different processors are trying to write the same bit of memory at the same time. You get out-of-order things. What if someone's just overwritten the thing that you were trying to read? How does all that work? And so to solve that, you have to worry about locks and things like that. But the really big problem with writing to shared memory programming models is that they only work on shared memory systems. And that's fine if you're only ever going to run them on shared memory systems. But the biggest systems and the most flexible and the most powerful systems are distributed memory. And the reverse isn't true. If you write for distributed memory systems, you can run them on shared memory systems, which is why I think MPI is an interesting thing for us to look at. So, so this is also known as symmetric multiprocessing. And the symmetry is about the fact that all the bits of memory are the same speed for all the processors. There's another variant of this called non-uniform memory architecture, where the processors come in blocks, and there's the block on the right is exactly like the thing we just looked at. It's 4 processors talking, with a memory bus that they can use to talk to the memory, and the same on the left. But the processors on the left can't get quickly to the memory on the right. They can get there, but they have to go through another interconnect through the processors or through something, and it's slower. And so it's non-uniform, because this memory is fast for these 4 processors, this memory is fast for these 4 processors, but this memory is slow for these 4 processors, and vice versa. And NUMA has never, there have been NUMA machines, and they're fine, but they're always a bit unpopular with programmers because they kind of have the disadvantages of both systems, because they have the disadvantage that they're non-uniform, so you have to worry about where things are. The disadvantages of both systems. What's the other disadvantage? Anyway, no one really likes NUMA, but they do exist. Unlovely children. There's a relationship between this and clustered and distributed computing. Basically, if that interconnect is not like a tight interconnect in a single box, but is a local area network, that's really what a computing cluster is, typically. And if that interconnect is really the internet, then that's really what grid computing is. And you can still solve problems across it. All the loosely connected things, like you're probably familiar with the SETI at home screensaver, where people gave up spare cycles on their systems to look for extraterrestrials, or there were various, I think some of the medical people got involved in that, and we looked for cancer and stuff like that. Or maybe it was gene sequencing, something like that, anyway. Okay, but where it's really at, even though physically this isn't where it's really at, but what we're going to talk about, the programming model we're going to talk about, is for distributed memory. And with distributed memory, I don't know if it's what it sounds like or not, but every processor has its own memory, and that memory is private to that processor. And so processor 1 has its memory 1, processor 2 has its memory 2, and all the rest of it, but they can all talk to each other through a messaging system. And so you just have to arrange your computation in such a way that you do most of your computation on your local stuff, and when you need stuff from someone else, you pass messages to get access to that. So either you ask someone else to send you some stuff, or they just proactively send you some stuff because they know what you're going to need. So the pros of this are that there's no contention to worry about, because only you have access to your stuff. You can use, this is very important, you can use this, if you program for distributed memory, you can run this on a shared memory system, and all that happens is you partition up the shared memory and say, well, actually, we're going to treat this as if it's your private memory. And then message passing just becomes copying in local memory, so it's actually even faster. It's in some sense better on a shared memory system than on a distributed memory system, because it's typically lower latency. And it's very scalable. You can build much bigger distributed memory systems than you can shared memory systems. These are sometimes called shared nothing systems, which is complete nonsense, because you can see from the diagram that they share stuff, but anyway, whatever. Cons, well, arguably it's conceptually harder. I don't know that I buy that, but people seem to find it conceptually harder. It does involve message passing, which involves copying and some latency. And there is the potential for deadlock. And if you do ever install MPI and try writing programs in the system, you will definitely experience deadlock. Though I did have a surprise when I was preparing this, when I wrote a program that I thought was guaranteed to deadlock, and the bloody thing didn't. But anyway, we'll come to that. So what's MPI? Finally, nearly, finally. How am I doing? God, that's not bad. MPI is the message passing interface. It is a high-performance, general-purpose message passing interface. It's extremely mature. The proposal for MPI, for the first version of MPI, was 1991, and it was implemented basically in 1991, and it built on other stuff that's even older than that. I think it's true. Last time I checked, it was certainly true, but I think it's still true that the vast majority, on any sensible way of counting, the vast majority of large-scale scientific parallel computing uses MPI. It's almost all of it at scale, the really big stuff. It is perfect for distributed memory parallel computing, but it's remarkably good on shared memory systems as well, where, as I say, message passing just becomes local buffer copying. So I think there's a big advantage in writing using MPI, even if you're going to run on a shared memory system, which, let's face it, most of us are most of the time. There are two main implementations, OpenMPI and MPI-CH, and they're the same. I couldn't even tell you which is better than the other. They both work. They're both fantastic. I suspect you'd struggle to know which one. I think one of them's slightly more standards compliant, and one's slightly faster, but they're both great. Okay, do we have time for a historical interlude? We'll do a very brief historical interlude. It's really just me indulging myself. But given that you haven't actually installed MPI, we've got time anyway. So back when I started at Edinburgh doing a PhD in physics, and we had these funny parallel computers, we got, as I said, this Mako computing surface. And they were built out of transputers. Now, transputers were whole systems on a chip. Systems on a chip, we talk about that today. They were these little packages that had a processor and a bit of memory and 4 communications links, and you could bolt them together almost like Lego. You actually typically got a board which had 4 of them, and some of the links were set, but there were sort of 8 links pointing out of the board. And you could reconfigure them in software. But the point is, each processor only talked to 4 other processors directly. And in particular, in this particular wiring diagram, processor 1 isn't connected to processor 6 directly. So if it wants to talk to processor 6, it has to go via some other set of processors to find a path that works. And so what happened in the beginning was people actually wrote complicated programs that figured out how to route their messages to where they needed to get to and all the rest of it, and tried desperately to arrange things so that the topology of the computing grid matched the topology of your problem, so you only ever had to talk to your neighbors, which is by far the most efficient thing anyway. But a rather brilliant guy called Mike Norman said, this is all too hard. I should just work really hard and write a program that puts a post office on every transputer, and then when you want to send a message, we'll just give every processor an address, and you just say, I want to send a message to processor 3, and the post offices will all talk to each other and make it happen. Okay? And that was called TITCH, the Topology Independent Transputer Communications Harness. And it was fantastic. It was incredibly slow. It required 7 buffers on every machine to work. But it was an amazing proof of concept. And so then Lyndon Clark came along, and TITCH begat Tiny. So TITCH was written in Occam, which was this weirdo intrinsically parallel language based on Tony Hoare's communicating sequential processes model of parallel computing. Tiny was exactly like TITCH, except it was written in C instead of Occam, and it was fast, and I think it only used 2 buffers. So that was TITCH begat Tiny. And then in 1990, we formed the Edinburgh Parallel Computing Center, and Tiny begat Chimp, the common high-level interface to message passing. You can see a lot of work was put into these names. Chimp was also written in C, but it had bindings for Fortran, and that was incredibly important because although everyone in this room thinks Fortran died about 100 years ago, actually Fortran is still the most common language in scientific computing, and a huge amount of the work that EPCC did used Fortran, so that was super important. And then in 1991, Chimp was one of the inputs to MPI, the message passing interface, which became an international standard and which is the MPI that we still use today, right the way back in 1991. Now, from an Edinburgh point of view, this is not a neutral presentation of how MPI developed. But if you were in Edinburgh like me and the only people you knew were the people who wrote TITCH and Tiny and Chimp, as far as I can tell, there was TITCH and Tiny and Chimp, and then it got renamed MPI, and that's what we use today. apparently these Jack Dongarra and Tony Hay and all these other places, they had ideas too, and they all probably contributed lots to MPI, and I'm absolutely certain they did, but I don't know what those bits were. As far as I'm concerned, it looked like that. So, end of historical interlude. Edinburgh's great. You should come there. It's really beautiful, and it's not as hot as here. Okay. Half an hour. That's pretty good. We're going to have time for you all to do hands-on stuff using the code you haven't installed. Okay, before we, that probably is actually not bad. Are there any questions at this point before we actually start looking at how you program with MPI and all that kind of stuff? Is this okay? Am I going too slowly or too fast? Or I can't really go back and change it, but I could change the next bit. I could do the next bit in parallel or something. Have we got another screen? Okay, no questions. Well, that's either good or bad, or neutral, I guess. Okay, so the main way, if you read the MPI documents, and in particular if you read the MPI for MPI for Python. So as I say, there are two main implementations of MPI, and they both have bindings for essentially every computer language that matters. And that's not me being dismissive of computer languages. I mean, they have, I don't know how many languages they have bindings for, but it'll be like 30 or 50 or 100 or so. It's absolutely huge numbers. You can basically use MPI with any reasonable programming language you might want to use it with. The Python bindings for MPI, the main version is called MPI4Py, which is maintained by this Egyptian guy whose name I have forgotten but is on the slides later, Lysandria or something, I think. And the standard way of running an MPI program in Python is not to run Python directly, but is to use a program that gets installed when you pip install MPI4Py, which you can only do after you've installed MPI, to use this MPI wrapper, which basically you say MPI exec, saying I want to execute something using MPI. You tell it the number of processors that you want to use, which is typically the number of processors on your system, and it should be the number of hardware processors, not any virtual processors. So 4 would be a good answer for a lot of people in the room. A few of you might have 8 processor machines, some of you might have 2. And then you give it the command you want to run, which is, in this case, Python foo.py, if foo.py is a program that uses MPI4Py, and therefore MPI. So for example, when I run Miro's tests, which is one of the things that I regularly, Miro is the software package that I do most of my work in. When I run its tests, I have a script called ptest, and this is what I run. There is a thing I tend to run on Macs, and it sometimes doesn't exit cleanly because of some bug somewhere if you don't set this variable ompimca btl to self-TCP. I have no idea what any of that means, but it stops the errors happening, so it makes me happy. I actually have that set in my .bash RC as well. And then I time it, and then I run MPI exec -n, and then this sysctl -n hw.physical CPU tells you how many cores there are in your system on a Linux or Macintosh system. I don't know if there's any Windows in the room. I don't know how you find out programmatically how many processors there are on a Windows machine, but I'm sure there's a similar way of doing it. And so this says, so on the laptop I've got here, this returns 8, and so it will run 8-way parallel like that. And then Python 3 or Python or whatever, this can be whatever the path to your executable Python is. It doesn't have to be anything in particular. I do tend to say -m MPI4Py, but you don't need that actually. And then ptest, which is ptest.py, which is my parallel test script, and then whatever else I put on the command line gets passed straight through. So that's in general how you run an MPI program. It is possible, and in fact I prefer to just run a Python program and then to spawn the processes from within Python dynamically. But we probably won't really get to that today. But it's important to know that that's an option too. And if you did want, I'm sure there's no one in the room who does this, but if any of you, for example, I don't know, spend an unhealthy amount of your life in Jupyter, you might find running it with MPI exec inconvenient, and you might prefer running it directly from Python using dynamic process creation. So that's a thing. Okay. MPI. Let's look at the simplest MPI program. This is a simple MPI program, so we'll go through all of it. So the command at the top is how you run it. Obviously, it says -n2, but it's -n however many processors you've got. Or well, no, in this case, you really do want to run it with 2, actually. So we import MPI4Py, or rather, we import the MPI object from MPI4Py. which is just a global that we have. And then we create, or rather we get access to a communicator, which is actually an intercom in MPI speak, as MPI.com world. So this is the thing that we use to talk to other processes. We can talk to any other process or processor in the system using this communicator. And we do a get rank, and the rank of a process in MPI is just your processor number. So if you run with 4 processors, there will be a process 0, a process 1, a process 2, and a process 3. They always start from 0. They're always contiguous. That's guaranteed. It's not assuming anything. That's just how MPI works. And so in this case, what we're then going to do is a switch that says, if my rank is 0, then I'm going to send a message. And if my rank is 1, I'm going to receive a message. So this process is just going to send a message from process 0 or processor 0 to process 1. I'm not really going to distinguish between processors and processors. In MPI, you almost always want exactly 1 process per processor. Certainly for any simple use, that's what you want. So on the 0 process, we just construct a message. It's just a string. It can be any pickleable Python object. If you don't know what pickling is, we might talk about that later. But any regular Python object is going to be fine. And then we say com.send. So we use the intercom to send this message. We tell it what we want to send. The thing we want to send is our message, which in this case is a string. But even though I've called it message, it doesn't have to be a string. It could be an array of numbers. It could be an object. It could be a fairly complex thing. It could certainly be a dictionary, for example. And we tell it where it's going to go to. And so we want to send it to 1, because, well, I'm 0, and I want to send it to 1, and we've only got 2 processors, so that's the other one. And so that's all that happens on processor 1, except it tells us what we've done. And then we say, otherwise, if rank is 1, which is the only other possibility, we do a resv, a receive, and we wait for a message. And we can tell it where we want to get it from. Actually, we don't need to tell it where we get it from. If we don't put in that source equals 0, it will just accept a message from anywhere. So we can use this to determine if several messages are coming in, which one to get. But that's what's going on. And then we print something there. And when I run this, this is what happens. But given that you haven't all... So, well, if... Oh, no, I'll say a couple of other things, this stuff on the side. So both intercom.send and what I've written as intercom.receive, but should be intercom.recv, sorry about that. It's amazing how much more visible mistakes are when they're on a big screen then. These are blocking operations. What does blocking mean? Blocking means that, it doesn't mean what you think it means even. What do you think blocking means?
The execution stops there
until it's finished. Okay, anyone else?
The rank 1 stops there until it receives the message.
Yeah, that's what you'd think it means, wouldn't you? That's what the name suggests. That's not what it means. It almost means that, but it means something subtly different from that, just to, really confuse you. It blocks until it's safe for you to overwrite the data that you're sending. It does not necessarily block until the message has been sent. So when it comes back, it doesn't mean the message has been sent. You will think it means the message has been sent. You will often act as if it means the message has been sent, but it doesn't actually mean that. It just means it's safe for you to overwrite whatever you're doing. So if you've got some mutable array that you're passing, you can mutate it further, and that's fine. That's what the blocking is about. So it does block. It blocks for a period of time, potentially. But it decides whether or not it's going to take a copy of the thing and then give you back control and send it later, or whether it's actually going to wait until it's finished sending it. And the general rule of thumb is if it's a small thing that you give it, then it will copy it and hand back control almost immediately. But if it's a big thing, it will, because it hasn't got too much buffer space to spare, it will wait until it's actually sent it. So you don't know, and that's one of the places everyone gets tripped up in MPI. The receive is a blocking receive as well, and that does mean that it blocks until the variable's actually been filled in. So now that we're a bit later, who's got a working?
As a follow-up, with conda install MPI4Py, it gets installed directly. I don't have to do anything else. But did you try the scripts? Yeah, they're working for me.
Oh, wow. That is absolutely worth pausing on. Well, those of you who already, we will pause, but those of you who already have it working, if you've cloned the thing, you could just run this script, or you could type it. Typing is really good for you, even if you don't type it now. Go home and type it afterwards. I know it sounds stupid, I know it sounds like a waste of time. Your fingers learn things, your brain learns things by doing, not just by git cloning. I will run it, and then we will have a little interlude where we all try and install it with Conda. Those of us who've got Conda installed. So I have a terminal here. Am I in the right place? I'm in the right place. So if I say this, and it tells us that processor 0 sent the message, dear 1, hi, love 0, and processor 1 received a message from 0, dear 1, hi, love 0, which is about as fantastic as things get. Not that I want to downplay expectations for this session, but... So that's a basic blocking send and receive. My friend, what's your name?
Juan Luis.
Juan Luis. Juan Luis. Would you like to, could you give Juan Luis the microphone? Could you tell people the magic incantation to get everything working without compiling MPI from source?
The MPI4Py is basically compiled already as a conda package. So if you do conda install MPI4Py -- channel conda forge, it works. You don't need to compile MPI or anything like that.
I can help, he says. So say it again. Conda install? Conda install?
Yes, conda install MPI4Py -c channel, yes.
Minus C?
Minus channel, sorry. Conda dash forge.
Like that.
Yes.
Okay, I'm not going to do that, because I have a working MPI4Py, and I'd quite like to keep it that way. Not that I'm suggesting anything would go wrong, but if you don't have a working MPI4Py, you might want to try that. I'll leave that there just for a couple of minutes. We're making such brilliant progress. We can afford to take 5 minutes and let people try and install it. I could tell jokes. What? No, maybe not. See the one about how Dominic Raab thinks it's not clear why the ethics advisor resigned. I mean, aren't barristers supposed to be able to read? Oh no, if I do that, that's not going to help, is it? Yes. That's very simple, isn't it? Conda install MPI4Py -- channel conda dash forge. Yes?
I just have a quick question.
Is Juan Luis wrong? Does it not work?
No, I don't.
Oh, okay.
I'm just curious if like the rank 1 before the rank 0 here,
Yep.
what would have happened?
If you swapped it,
Yeah.
try it. But nothing would happen. It would be exactly the same. There's no difference between 0 and 1. They're entirely equivalent.
Okay.
It's just the message would go the other way. But you don't know which one's 0, which one's anyway, so it's kind of... So it would be fine. You can try it. That's a good change to make. So the question was, what would happen if... I'm going to try and leave it... So that's still visible. What would happen if we swapped 0 and 1 in this program? The answer is nothing, or rather, you wouldn't detect any difference at all. Well, you would detect a difference, which is that it would now be lying when it said, dear 1, hi, love 0, because really the message should be, dear 0, hi, love 1. But other than that, but it wouldn't change. So actually what would happen was, I suppose that is the change. The program would lie. And it would say that it would suggest that 0 had sent a message to 1 and that 1 had received it, whereas what would in fact have happened was 1 would have sent a message impersonating 0 to... Anyway, but no, it would work exactly the same. And you should try that. If you have a working MPI4Py, try that. And my prediction is the output will be... oh, well...
Actually, you were trying to send it to yourself, right?
Oh, sorry, if you swap that, but you don't swap those.
Like it was more if we tried to receive before sending.
We'll come to that. No, that's a different thing. But it's not a question of before and after here. What's happening on processor 0 is it's doing a send, and what's happening on processor 1 is it's doing a receive. And the whole point of parallelism is they're happening out at the same time. On processor 0, only this part of the code executes, and on processor 1, only this part of the code executes. So it doesn't matter if you... Right, so another thing is, what if you put the if the other way around? If you put this branch first, it wouldn't make any difference at all. But yes, if you do... Well, you're keen on this deadlock thing. If you try to receive before the send, potentially things... Well, it's not even so much which order you do things. It's really nice in MPI. In fact, not just nice. It's sort of necessary for things to work that whenever one processor sends, the other process receives, and whenever one process receives, the other one sends, because especially with blocking stuff, otherwise they'll deadlock. If you do non-blocking stuff, which we are going to talk about too, you still really fundamentally need that, but you've got a bit more flexibility about the order of things, which is what we'll see in a moment. Okay, has everyone at least copied that typed conda install MPI4Py -- channel conda forge? I'm going to assume you don't have that installed and working yet. MPI, really? What about MPI? Try MPI run. MPI run is exactly the same as MPI exec, except for small differences that, no? But that worked for you. Yep. Works on my machine. It seems to me that the conda installer is broken if it doesn't give you MPI exec, because you need that. It could be a path issue, obviously. So it worked for you. It didn't work for you. Who else has tried? And it worked? It's not looking good at the moment.
Didn't work with me.
Didn't work with you. Okay, so that's 2-2. We could, if I had a pen, I've got a pen actually, but I suspect they're not going to like it if I start writing on here. Okay, so 2 works, 2 didn't work. Any advance on?
Yeah.
Worked.
I also tried to reduce my processes to 1, and therefore I didn't have them. And I get a different error code.
Ah, well, you would.
It was good. It told me what the error was, so I was quite pleased.
There you go. That's you see, you can tell Emlin's a PyData organizer. He thinks of things like that, trying random shit and random stuff and good. Okay. I am not qualified, and we don't have time to try and diagnose what's going wrong. But at least we have more now. We could start doing the thing where people gather around the screen and see if it works for other people and stuff. Okay, that was the simplest one. How are we doing? What have we got to? We've got to 4:15. Okay. So this is kind of what we're talking about. So the way you conceptualize this is probably, and the way almost everyone conceptualizes this is that you do the send, and what happens in a blocking send is that it waits for process 1 to initiate the receive, and then sends the message, and then returns control, and then it does the print, right, on processor 0. And on processor 1, it waits for process 0 to initiate the send, and then it receives the message, and then it returns control to the calling program and does the print. And that might happen. That does happen some other time. If the message was big, that probably is what would happen. But as I say, the call blocks until it's safe for you to overwrite the data, not until the operation is completed. And it is quite important to bear that in mind. It may copy your object and then return control for you, or it may wait until it's been sent. And actually, there is a way to influence it, but again, that's like a more advanced topic that we're not going to worry about. But you shouldn't need to know, is the point. What matters is whether you can mutate the data, because you're not really going to do anything with your knowledge about what the other process is doing. With blocking receives, the call blocks until it's complete, and when you regain control, you're guaranteed that the transfer is complete. So you do pretty much know that return has been controlled to the sending process as well. You don't absolutely know, but it seems very likely. Okay, but here's another possible timeline, therefore. So what could happen is that you do the send, MPI copies the message, it returns control to you, it prints that it sent the message, then it waits for process 1 to initiate the receive, then it sends the message. And that's completely valid as well, and it won't look any different for you as long as you write a correct program. There's another minor variant, but it's not really very different, so it doesn't matter. So in general, so this is how blocking works, and it's It's often easiest to start off doing blocking communications. You can normally write a version of the program that works with blocking communications. But the problem with blocking is it introduces idle time, i.e. the computer waits around blocking, not doing anything useful on that process. And that's detrimental to performance. But it does make the code easier to reason about. The downside of blocking, apart from performance, is that it creates the conditions for deadlock, which is, I think, what you were worrying about. What happens if you do a send and no one receives? And you often need to use, it's often a good idea to use some non-blocking communications both to reduce idle time and to avoid deadlock. And it's important to realize that you can do a blocking send with a non-blocking receive, and you can do a non-blocking send with a blocking receive, or you can mix them however you like. Yes, sorry, there's a hand.
I was wondering whether the deadlock occur because of a bug in the code, or because sometimes you send a message and it gets lost.
Okay, so the question was, does deadlock occur because of a bug in your program or because it gets lost? So on correctly functioning hardware and correctly implemented MPI libraries and MPI4Py, it's always because of a bug in your program. And in practice, it's almost always because of a bug in your program. One of the super frustrating things about parallel programming in general is that you can write code that works. And you can run the tests 1,000 times, and you can run it on all sorts of different systems, and it's fine. And then suddenly, it doesn't work. And quite possibly, it never works again. That's certainly how it feels. And all that's happened is your code was always wrong, but you were lucky the first, 999 times you ran it or something. This is one of those moments when I have to say, so I don't work at EPCC anymore. I did work at EPCC. That was like 25, no, it's probably more than 20. Anyway, it was a lot of years ago. I was slightly nervous that I might have forgotten some things about parallel computing, which I definitely had. So I did take the code that we're working on today in and get someone at EPCC to verify it. Now, that doesn't mean that if there's a bug in it, it's his fault. Obviously, it's completely my fault that I wrote buggy code. But just to reassure you, even if I have forgotten everything I knew 30 years ago, someone else thinks this code might actually be sound. But yes. OK, so now let's create Deadlock. So here's a program. Here's another program that we're going to run with MPI exec equals 2. With 2 processes exactly. So we're going to get my rank. So we're going to run the same code. There's no ifs in this. I'm going to get my rank, and I'm going to call that me. And I'm going to therefore deduce that the other processor's rank is 1 minus me, because if I'm 0, that'll be 1. And if I'm 1, that'll be 0. And then I'm going to create a message, dear other, hi, love, me. And then I'm going to send that message, and then I'm going to receive a message from the other one, and then I'm going to print them both. And it should be entirely obvious to everyone that this is a deadlocking program, because we both do a send, and we block, and then we both do a receive, but we'll never get to the receive because we're blocked, right? So, yeah, it's difficult if most of you haven't actually got working implementations. So I wonder if I should run it. Well, what I was going to say at this point, and I suppose I will still say, is you should copy your first program, because this is encouraging the typing thing, and modify it. It's quite similar to this. Modify it to look like this, and then run it, as long as you know how to kill processes on your system, because if you don't know how to kill processes, you might end up with a system that's a bit blocked. I mean, you could restart it, but you can just use Control-C or Control-Z or whatever on Unix and Linux and kill the processes. Yep. Yep.
Because you said that it would be blocking until the moment we can actually modify the state.
Yes.
Is that the case that you actually can send and then receive the one from the other?
Gold star. That's exactly right. I wrote this program fully expecting it would fail, and it didn't fail. It worked, and the reason it works is because these messages are small, and it does in fact copy, well, at least on my system, it copies them, and therefore it doesn't block. So I will run it. If you are, I really haven't thought this through, have I? If I run that, you're not going to be able to see the code anymore. But you've got a copy of the code locally anyway. I don't know, and most of you haven't got working things. So if I run that, because I have deadlock risk, and you might have noticed it's called risk. If I run that with this command, then what actually happens is it works fine. I shouldn't have said that before I'd run it, had I? It might work fine. And in fact, it did work fine. And the reason it worked fine is exactly, sorry, what's your name? Thomas. And it's exactly for the reason Thomas said and that we started talking about, which is that although this is obviously an unsound program, in fact, I would say this is a buggy program, you would certainly expect this program to fail a lot of the time. You certainly would never rely on this program working because it has no right to work. Actually, it will work because that message is short enough that almost all MPI implementations will copy it, return control, so they'll both do the send, they'll come back, and then they'll do the receives, and then that will allow the sends actually to happen, and then it will finish. So we haven't actually succeeded in creating Deadlock. Even though it turns out Deadlock's really easy to create, and you will, if you do anything with MPI, you will definitely succeed in creating Deadlock, but just not quite this easily. Now that was slightly subtle, even though Thomas worked it out. Would it be helpful to anyone if I went through that again? Yes. And what one hand going up means is that probably half the people in the room would benefit from it. So we'll do it again. So what you think is happening, just from kind of the language, is that you think this is sending a message, well, constructing a message, sending the message, waiting until that message has been sent. And because both processes are trying to send, it obviously can't work. But it does work because MPI has freedom when you do a blocking send to copy the message that you're sending into a local buffer and then to return control to you, and only to send it when it's able to do that. So what actually happens is because this is small, it actually does copy the message. So you do the com.send, it copies your message to a buffer, it hands control back to you, then it does the receive, and that's happening on both processors. And so now they're both waiting for a receive, a blocking receive, but that blocking receive can happen because the other end, there's a send ready to go now, and MPI uses interrupts to take back control and all the rest of it and sends the messages, so it does work. Well, it might not work, but it works for me. Emlyn, does it not work for you?
Confirm to make the message bigger or the same. Arbitrarily make the string larger.
Have you been reading ahead?
No.
Good. Gold star for Emlyn as well. So, oh, good Lord, there's a slide about this. Well, we've talked about this anyway. It's 19 characters. It's about 75 characters, including all Python's overhead. When you pickle it, it gets very slightly bigger, but it doesn't really make any difference. So, let's force Deadlock. Emlyn's already done it by forcing it to be bigger. Did you do it by doubling the message size each time till it failed?
No, I took the letter A and multiplied it by 100,000. Added it to my string.
Well, there you go. So here's a I'm not going to say it's more scientific than that, but here's a way of diagnosing it further. So what we're going to do is almost exactly what Emlyn did. We're going to keep multiplying our string. We're going to multiply not A, but our whole message. So we're going to do a string of length 19, and we're going to multiply that by 2 to the n for different values of n going up through a loop and see what happens. So it's essentially the same code. So again, in my enthusiasm for getting you to type things, because typing is really good for the soul unless you've got RSI. Well, it's still good for the soul if you've got RSI. It's just less good for your fingers. Is to copy the previous program and put a loop in and do all this stuff. But again, because not absolutely everyone has got that. Have you already implemented the task farm yet, Emma? Have you already implemented the task farm as well? I just thought you seemed to, just seemed to be on the golden path. So I will show you what happens if I run this program. You notice I'm not taking my advice and typing it, but I have typed all this code. Well, with a bit of help from copy and paste, obviously. So Deadlock, to Deadlock. What happens if I run to Deadlock? How does it say to run to Deadlock? You can see I'm so keen on typing, I'm not going to risk typing the command. So what happens is Things don't necessarily come out in the right order in parallel processing. That's another thing, because all that contention stuff I was talking about, that's still true for screen output if you really are stupid enough to have printing going on from lots of processors, which is fine during debugging, but not very good in real life. So processor 0 sends 4 messages, a 19 and a, no, what? Oh, no, I'm sorry. Processor 0 sent a message of 19. It received a 38. It sent a 90. Processor 0 sent a 19. Yeah, there you go. Oh, did it start at 2 to the 0? It probably started at 2. Anyway, whatever. It succeeds with all the little ones. But then as they get bigger, eventually it gets 2. So it succeeded in both directions with 2,432. But now it's hanging, it is deadlocking. And my God, is it consuming power. Did everyone get the bit about bring a power adapter? Because one of the things, these machines are very highly optimized to use almost no power at all. And then we run MPI on them. And they run all the cores all the time, maximum speed, and then they deadlock. And even though you might think it's not doing very much work, deadlock takes a lot of work. So at this point, you either type Control C, which might work, or might not work. Yeah, it worked here. And if that doesn't work, you normally type Control Z, and then you've got stop jobs, and so you do kill % or whatever, and that kills your job. So it looks like, so that's a message of length, 2,432, and it's a 19-character message, and there's a little bit of overhead for the string. So that's probably saying that it broke about 32K. In fact, there's a very good chance that it broke exactly 32K, because that's probably what MPI4Py uses as the maximum buffer size it copies. Has anyone else, I know Emlin's run it with an A variant of this. Has anyone else succeeded in running that and seen it hang? Okay, so that's the deadlocking version. Oh my God.
I used to see like if I put a super long string in the 0, so the first program, and it's very fast. Even if I put by A by 1 million, still completes very quickly. The other one, not the deadlock one, but the previous.
Oh, in the okay, yes. No, that's fine because it's only doing a copy. Yeah, so it should be fast. Okay, so we've succeeded in creating, it's a bit sad that the first thing I try and teach you to do is to create deadlock, but the point is you need to know how to avoid these things. There was a hand.
Yeah, a question.
Yeah.
What do the cores do while there's a deadlock? Are they idle and they do other stuff, or their stuff?
Experience suggests that they are not idle and that they're in kind of a spin loop and that they're working pretty hard and can't do any other stuff. We could, but why don't we do a scientific experiment and find out what happens on a Mac by running Activity Monitor and seeing what happens if we run that program again. You could do this yourself. So both cores are running at 99 point something, or 101.1% of one CPU. This machine is so parallel, it's incredible. Yeah, that looks like it's pretty busy to me. So yeah, you probably don't really. I mean, actually, really deadlock it. I mean, I know it was fun to create it, but it's like the bit where you cut yourself a bit and then learn that if you pushed a bit harder, your whole thumb would come off, and you don't want to do that anymore. So it's why your dad told you should whittle sticks, or maybe your mum told you should whittle sticks.
They constantly check whether they can send or whether they can.
Yeah, I think they're in a busy loop. Yeah, actively trying to do stuff. Yeah. So yes, which is why one of the important prerequisites for this thing was to bring a power cable, because you will be desecrating the planet during this session. Okay, were there any other questions? Or okay. Now, it obviously might be different on your machine. Different systems might have different buffer sizes, and in particular, different MPIs might have different buffer sizes and all the rest of it. But I think MPI4Py uses a 32K cutoff for that buffer. Okay, let's talk about non-blocking communications. So there are non-blocking counterparts to intercom, which should have a capital I. Sorry, we'll just fix it while we're here because because then it'll be better next time round when you all come next year and say, I didn't understand it last year. Or I didn't have MPI4Py. Oh, for God's sake. There you go. So there are non-blocking counterparts to both send and receive. And with the non-blocking versions, you initiate a send or you initiate a receive, and what you get back is a handle. And that handle you can then wait on, or you can either test to see whether that operation's completed, or you can wait on it and then it will block until it has completed. But what that means is that you can initiate a non-blocking send or receive, do some other stuff, and later at a point where potentially everything's set up, you can come back and wait when you actually need the result of whatever it was you were doing. So the non-blocking versions just have an I in front of them. So iSend is a non-blocking send, and iRecv is a non-blocking receive. So the general form of a non-blocking send is you say request equals com.isend data and wherever you want to send it to. And then at a later point, you do a rec.wait, and when that comes back, you know that you can overwrite the buffer and that everything's completed. Well, you know that you can overwrite the buffer, I guess, more specifically. And in the case of a non-blocking receive, you do request equals com.ireceive, potentially do some other stuff. And then if you're not going to do other stuff, there's no point. You might as well just do a blocking version. And then you say data equals rec.wait, and that will return only when data's been filled in with the result of that receive. Okay? So, oh yes, this is probably my favorite slide. A non-blocking receive can receive a message from a blocking send or a non-blocking send. A blocking receive can receive a message from a non-blocking send. So if you like Boston boxes, and everyone likes Boston boxes, except me, I hate Boston boxes, but this is my favorite ever Boston box. This is the compatibility matrix for blocking and non-blocking sends and receives. And it's all good. You can still get deadlock, but that's a different thing. It's perfectly legitimate to do this, and it will work if you write correct code. So write correct code and you'll be fine. Note. Yes. So the guy who maintains MPI4Py is, in fact, Lisandro Dalcin, or maybe it's Dalcin, I don't know. He's an Egyptian fella. And I didn't understand why things weren't working as I was preparing these slides. And I found this comment from the guy who writes MPI4Py, which might put you off MPI4Py. It's better than this makes it sound. But what he says is the implementation of iris for large messages requires users to pass a buffer-like object large enough to receive the pickled stream. This is not documented as most of MPI4Py, and even non-obvious and unpythonic. But if you have some good knowledge about MPI, you'll understand its limitations for implementing iReceive for pickled streams. Which is not super encouraging, but what that's really telling you is that if you don't know that your message is going to be small, and in particular is going to be less than 32K, that same magic number, you actually have to give MPI4Py a buffer to receive into. And you do that by creating a byte array. It's always a byte array. It doesn't matter what kind of data you're sending. This, he's suggesting a 1 megabyte byte array, which is what this creates. But you need to provide it with a buffer, and you just provide that as a first positional argument. And then everything proceeds the same way. So you need to note that, and if you don't note that, you might be sad. So buffers and pickling. So send, iSend, receive, and iReceive can work with any pickleable Python object. What's pickling? Who knows what pickling is? Wrong question. Everyone knows what pickling is. Who doesn't know what pickling is? Is there anyone? Excellent. There's someone who doesn't know what pickling is. That means half of you don't know what pickling is, in my experience. Pickling is serialization. We have structures, like real structures, like not the type on this slide, but like an actual Python structure that is a dictionary, A maps to 1, B maps to 2, or whatever. And those are structured objects, and they can't just be sent down communications channels. Communications channels just accept bytes. So the process of marshalling in general and serialization in general, and in Python pickling, is the process of taking some complex structured object like that and turning it into some kind of byte stream. Doesn't really matter what it is. That can be sent down the channel. So turning it into a string, but not even just a string, not a Unicode string, an actual byte string, bytes object. That's what pickling is, and loads of stuff in Python is that. Most Python structures can be pickled. You mostly get into trouble if they have sort of mutual references within each other. So if you have two things that point to each other, it can be quite difficult to pickle those. But in general, most stuff you can do is pickleable. There's a standard, the part of the standard library is the pickle function that is used when you want to take some data structure and write it to disk. And many of you will have used that. And that's what happens behind the scenes when you pass Python objects using MPI. Now there's these four methods that we've learnt about so far, send, receive, iSend, and iReceive. There are corresponding versions that have a capital letter for sending raw byte buffers. So things like NumPy arrays that are already in C land and don't have all the Python overhead, you can send directly using the capitalized versions of these, and that's much faster because they don't need to get pickled. So that's what's going on there. We're not going to look very much at doing stuff with NumPy today, but absolutely one of the really major use cases for MPI in Python is to send NumPy arrays or similar things or raw byte streams. It will be faster, and there's no point in parallelizing slow code, so you should be using NumPy or whatever is fast beforehand, so you've probably got those objects kicking around. And you should definitely use the capitalized versions of them if you're doing that. So now let's modify the code. Emlyn's probably already done this and created a buffer that's exactly one bigger than his array, probably forgetting the fact that he's got to add the Python overhead of 26 characters or whatever it is. No, 51 characters or whatever it is. Anyway, probably not forgetting that at all. So here's a version of it that tries to get round the problem by using non-blocking sends and non-blocking receives. And because of what we read on Bitbucket from Lissandro, we're going to create a buffer. We're going to make that buffer a megabyte, which is easily big enough. We could figure out how big it actually needs to be, but a megabyte's not particularly excessive. And so what we do now is basically the same thing as before, but now we do a non-blocking send, and we collect the request, and we call that rrec. We're doing the receive before the send, but we could do it the other way around. It wouldn't matter. We do the send, and then we wait on the receive, and when that's finished, we know that we've actually got the data, and we can print stuff. And then a crucial thing that almost everyone tries to get away with not doing, but it will make you sad if you don't do it, is even for sends, you do need to call the wait, even if you don't want to overwrite the buffer. Otherwise, your program will develop a memory leak, and memory leaks are really bad, and you want to avoid them. So you always want to wait on sends, even if you don't care whether it's been sent or whether the memory's available for reuse. You need to do it just as a bookkeeping thing. You can do it later, but you don't want to leave it, you don't just want to like build up all your sends and do them at the very end of the program or whatever, if you're doing a lot of them, because you'll leak memory like crazy if you do that. So this version of the code, the main point isn't the buffering, that's just an implementation detail. The main point, the buffering in the sense of creating the buffer. But because we're using non-blocking sends and receives here, this is guaranteed not to deadlock. Well, guaranteed. This is a correct program that should not deadlock, unless, of course, there's a bug, and it's not a correct program. But I believe this to be a correct program that won't deadlock. So those of you, which is probably most of you by now, who've got a working MPI4Py, how are we doing for time? Oh, 22, bloody hell. I will run this very quickly just to prove that everything's as I say it is. And then we'll get on to all the really exciting stuff. 20 minutes, that's not going to be enough to do the rest of the stuff. That's not how I run this. MPI exec minus n, it's just 2, isn't it? And it all ran through right up to 622,592 characters, not characters, well, characters, yeah, characters in the string, that's right. And even more than that, including the Python overhead. And it all works fine. Oh, and it's falling off the bottom of the screen, sorry about Okay, by all means carry on doing that, but I think we had better press on, otherwise we'll only have looked at Deadlock and not much else. So that all works, that's good. I get this error if I don't pass the buffer. So we've talked about that. Python objects need these versions. The capitalized objects will do byte arrays. As I say, Python's slow, and if you're one of the people who maintains Python isn't slow, I know all the arguments that Python isn't slow. Python's slow. Even though it's got fast libraries and you can write code and all the rest of it. So it makes sense to optimize code before trying to parallelize it, and using NumPy is often part of that. So all the examples I'm showing you today are stupid, but I hope I'm giving you enough information to allow you to use it for real on sensible things. There's some stuff which I'm not going to talk about, but you should generally specify types when you're sending NumPy arrays. MPI has a set of types that you can use. There are examples. They're available. So let's talk a little bit about data parallelism versus functional parallelism. So with functional parallelism, we take code and we allocate to different processes different functions, and we write kind of separate programs. So maybe one's, one's an oboe player, and one's a trumpet player, and one's a, whatever, or think of it how you like. And there's often some functional parallelism in programs, but functional parallelism's hard to scale because, maybe you can think of 4 different functions that it's useful for your code to do, but you probably can't think of 65,536 things. You probably don't want to write 65,536 separate programs or whatever. So what we mostly do is we use data parallelism. With data parallelism, we have either the same code, typically the same code running on every processor, or just a very small number of programs. And we're going to talk about task farm, where we have one special program that acts as a controller or a manager or whatever, and a whole load of workers that do all the work. And basically, they work on different data, is the idea. Data parallelism, so yeah, with SPMD, you can literally just, as we did in some of the examples, be running the same code on every processor without any branching. Or you can use branching to say, well, we'll run this bit on some of the processors and this bit on others of the processors, but nevertheless, fundamentally, you haven't got very much functional parallelism there. So let's talk about task farm. So it's probably the simplest general purpose parallel paradigm. They occur all over the place. Basic idea is that you have one process, one processor, which is given a collection of tasks to perform, and that, in the past, that was typically known as the master, but as with other things, we're trying to avoid words like masters and slaves, so we tend to talk about the controller, or the manager, or the main, or the distributor, or the queen bee, or whatever. But anyway, the controller who has the tasks, and then a whole bunch of workers who are there to do things. The manager allocates tasks to each worker, collects results from each worker. If there are results from the worker, sometimes they're just doing something and writing something to the file system or whatever. But if there's a result to be returned, it gets returned to the manager, typically. And then if there are still tasks left, when you return the result of your task as a worker, you get another task sent to you, and so on and so forth, until there are no tasks left, at which point a well-behaving manager will shut you down, and that'll be the end. With a task farm, usually the tasks are completely independent. So you might have to send some data to specify the task, but typically the workers don't then need to talk to each other. It's not impossible for them to need to talk to each other, but in a simple task farm, that's not the case. So we talk about embarrassingly parallel problems, which are ones where all the bits of it are just basically completely independent. And there are lots of problems like that, and they're perfect for task farms. So what does a task farm look like? So if we have 10 tasks, and we have a manager and 3 workers, because that fits on the screen nicely, what happens is the manager sends task 1 to worker 1, probably. And so worker 1 does that for a while, and then the manager almost immediately sends a task to worker 2 as well, task 2, and sends task 3 to worker 3. I mean, the manager might decide to allocate them in some funkier way than that, but that's what most managers do. And then at some point, the task completes, so task 2 turned out to be quite a little task. So these tasks don't all have to be the same size. This is one of the important things. And so a result gets returned to the manager, and at this point, we've got a result for task 2, so that appears up here. And now the manager being a bit of a slave driver, not that we're going to use the word slave, so the manager being a bit of a bit keen, immediately sends another task, task 4, to worker 2. And so worker 2 does that. And that turns out to be a pretty quick one as well. And so now we've got a result 4, and so worker 2, who's really grinding through the stuff here, but doing pretty simple stuff, gets task 5, and task 5 goes on, and so forth. And we just carry on like this. And so now we've got result 1 because that one's finished, and so now whoever was doing work. Oh, no, now also we get result back from T3 because there's stuff happening in parallel. It's like at the same time. It's amazing. And so now we've got result 3 as well, and then eventually the manager gets around to sending a task to worker 3, task 6, which turns out to be quite a big one, and also sends a task 7 to worker 1, and then task 5 finishes, and all the rest of it. And you see the thing carrying on. And so this is the general way a task farm works. It took me ages, this. I hope you're all really enjoying it. And I have to remember to stop, because if I go past the end, then it's very difficult to go back. But fortunately, I copied the output. So we end up with something like this. So one of the things that you see with this is that the whole thing takes longer than you might want it to, because we happen to allocate task 9, which is quite a big one towards the end. And so actually the only processor working at the end was processor 1 doing task 9. So if you can arrange for it this way, if you know how big the tasks are ahead of time, it can help to allocate the big tasks first so that all those get done early, and we try to avoid this situation. But what you can also see is that the total length of those lines, if you add, okay, there are idle times between the tasks when you're waiting for your next task, and you can do something about that. But what you do see is that the total length of the lines is a lot longer than the total length of the task here. So in this incredibly, I'd basically call this a mathematical proof. Task farms can speed things up, because the total length of the lines is more than the width of the diagram, which more or less proves it. You're going to suggest this isn't a perfect mathematical proof, aren't you?
No, I think it's flawless. But for task 4, I'm wondering, how does the manager know that worker 2 is free? Because it kind of sends the task 5 before it receives the result for task 4. So maybe it's just...
But task 4 has initiated the send before task 5 is sent, so I think it's okay.
How does the manager know that?
Well, that's a good question. It is possible that this animation wasn't an absolutely perfect implementation of a task farm. It's a good point. It's possible that there is some truth in what you're saying, and that it wouldn't work quite like this. Fortunately, my programming is much better than my keynote skills. So, yeah, good point. Okay, so how much of this do we want to do? We've got 11 minutes. We're not going to go through the task farm. I have printed out in glorious detail a task farm that you can run. You have the task farm here that you can use, and there's a stupid little example, and there are some exercises. The main thing that I think is interesting is, and Python, as Python people, you'll love this, how do you have a general purpose worker? And the answer is that you use all those features that we all love in Python, like star args and star KW args, and the fact that functions are first-class objects that you can pass around and stuff like that. So the way that in this task farm we specify a task is we give it a tuple, which is the list of positional arguments, and we give it a dictionary, which is the list of keyword arguments, if any, and those specify a task. And when we set up the worker, we tell it what function, we pass in the function that it's going to use to do the work. And then what the worker process does is just calls f on the positional arguments and the keyword arguments that you pass in the task. It splats them, so it passes star args and star KW args into the function. That does the work, produces the result, and that gets sent back. And at the end, we stop it. So I would love to go through this in great detail, but I think we're not going to have time. But you'll enjoy reading the code. It's really good. And Emlyn has already probably turned it into a one that gets rid of all those gaps and stuff. But this task farm is not quite the one that I use. I use a slightly more sophisticated one, but only a very slightly more sophisticated one. And I was going to show you some timings. So your exercise is to run the task farm, which just cubes the first 100 numbers. It's a stupid thing. The tasks are much too small to benefit from parallelism. But it shows you the thing. There are some exercises for you to do, though, in terms of, first of all, spit it. So at the moment, the code just runs under a protected if dunder name equals dunder main. Extract that into a separate file and run it and check that you can use the task farm as a separate thing, which you absolutely should be able to. Write some better functions, some bigger functions, and test whether it actually speeds up. Look at whether reordering the tasks from biggest to smallest makes a difference. In general, it should, if they're different sizes. And use it for real on something. I use it mostly. I have a huge bit of code that is basically an entire alternative approach to data science that uses NumPy but nothing else from Python. And I have a set of tests, about 2,000 tests for it, and I use a task farm to run those tests. I use almost this task farm to run those tests. And the laptop that I'm running here, which is an 8-processor Intel laptop, takes 3 minutes, 23 seconds, 203 seconds to run the tasks in serial. And if I run it with the task farm with 8 processors, which is 1 controller and 7 workers, so you wouldn't really expect it to possibly go any faster than 7 times, runs over 5 times as fast, which is pretty good. And if I run it on 4 processors with only 3 workers, it actually goes 3.1 times faster, which seems literally too good to be true, but I didn't do multiple runs and so on, so it's probably just performance variation. And in fact, if I run it on my supercomputer at home, my 20-processor Mac Studio, it runs in 10 seconds, which is pretty amazing. That's on 20 processors. It only takes about 90 seconds if you run it on 1 processor, but that's still, 50% of the maximum possible speed up you could expect pretty much, which is well worth having. And 10 seconds is a lot better than 3 minutes, 23 seconds to run a set of tests. So I'm quite pleased with that. Tests are easy. And the level of parallelism here is I have a bunch of different classes. It's just using unit test, and each class is a task, basically. And so in fact, I can almost certainly improve the speed up by breaking up the biggest ones into smaller chunks so that there's less thing. The version that I'm using is sorting from biggest to smallest, and that makes a difference. So you've got the code. Amdahl's law. Yes, Amdahl's law is important. Amdahl was, there was a computer company called Amdahl that made competitors to Craze. They were not as good as Craze, but they were pretty good. So the Amdahl's law says that the maximum possible speed up is limited by the longest sequential task. So if you've got hollow tasks in the task farm, obviously if one of them is going to take 2 minutes by itself, the whole thing can't possibly take less than 2 minutes. And later in the Mythical Man month, Fred Brooks made almost the same observation, saying 9 women can't make a baby in a month. There's a sequential 9 months involved in making a baby. So that's important. So what I'm going to do finally, is talk about the other form of parallelism in our remaining 7 minutes. Grid decomposition. So there's often a kind of grid or mesh of data over which calculations take place. So, in physics, that's like the atmosphere, or, a block of Earth, or a metal bar, or an aircraft wing, or whatever. And in, ecology, it might be, the Earth, or whatever, or a national park, or whatever it happens to be. The computation is often local, because physics is local, and even biology is kind of local, actually. Typically, there is quite a good degree of neighborliness, and you only really need data from where you're computing and a little bit around it. So breaking up that grid and having a distributed memory system, each have a different part of the grid and just communicate at the boundaries kind of works. And so with grid decomposition, usually each process, you usually just run SPMD. Every process does basically the same thing, or exactly the same thing. And there's basically a step where there's a bit of the grid that you're responsible for. You can typically update the interior of the grid, the bit that isn't bound at the boundary, the interior. You can typically do. But to do the bits at the edges, you need to get information about what the current state is of each of your neighbors. So Game of Life, a lot of you will know Game of Life. In fact, I've included in here a nice little copy of Game of Life. I'm sure most of you have seen it. So if I just run that. So there's a Game of Life running, doing all of those things. So you probably know Game of Life is a cellular automaton. So cellular automaton, so the black cells represent, so this is a grid, the black cells represent things that are alive and the white things are dead. And there's an update rule to get you from the pattern at time step t to time step t plus 1. And that update rule is that you count the number of neighbors that your cell's got. So looking at all 8 neighbors, the north, the west, the east, the south, and the northwest, the southwest, the southeast, and the northeast. And you count them. If the cell was alive at the current time step, then it'll still be alive next time if the total number of neighbors is 2 or 3. If it's more than 3, it dies from overcrowding. This is supposed to represent like a little, ecological system. And if it's fewer than 2, it dies of loneliness or something. Probably not loneliness. Maybe it's from not being able to mate. I don't know. Anyway, it dies. And if it's empty, then it will come alive at the next cell if there are exactly 3 neighbors. the update rule for game of life. And game of life turns out to be Turing complete. You can implement game of life in game of life, which is amazing. This is me counting stuff. I've probably counted it wrongly, so the guy at the back who counts things, yeah, it's probably wrong. You can mail me, or not mail me. With a grid decomposition, you probably can't see the red stuff, but if you've got 8 processes, you might chop it in, 3 that way and 2 that way. Sorry, into 4 vertically and 2, and then you've all got a thing. And then all of these would have 3, this one would have 3 neighbors to worry about. This one would have 3 neighbors to worry about. This one would have 1, 2, 3, 4, 5 to worry about. But if it was a bigger grid and you had more processes, then some of them would be interior and they'd actually have 8 neighbors to worry about. It's quite often simpler just to decompose in 1 dimension, actually. So you have less interior there is the downside, but you have less communication to do, so it's swings and roundabouts. Doesn't usually make a lot of difference. We're not going to have time to do this, but you can imagine the boundary communication stuff, it looks like that. Basically, at each step, you have to do non-blocking stuff where you send your boundaries to the relevant neighbors and receive the copy of their boundaries that you've got into your thing. You compute your interior, and then when all that communicates, you then block to make sure that all the communication is finished, and then you can update the boundary layer and go again. Again, I'm very impressed with my keynote skills here. I hope you are too. So this was good. This was good. When I thought this was a 3-hour class, or when I thought we'd get much further than we did, we were going to parallelize this using grid decomposition. But it turns out that a brilliant thing for me to do is to set an exercise for you. And the exercise is parallelize this using a grid decomposition. And I've broken it down into stages for you. First thing you should do is, so that thing that I ran, I'll run it some more because it's so nice. I've parameterized it for you too. So it's someone else's code. I found it on GitHub. There's a reference in the thing. We'll run it with, God, I can't remember what you give it. We'll run it with 100, and then it'll be bigger. Yeah, there you go. It's fantastic, isn't it? You've probably seen there are guns that shoot pellets, and there are all sorts of things you can put in game of life. You can see things moving about and eating each other and all sorts of stuff. Anyway, the basic thing that I've suggested, what have I suggested? It's written on the slides. Who's got the slides? So the rendering and the updating are all just totally merged at the moment in the code. So the first thing to do is separate those out and have a bit that does the rendering and a bit that does the compute. And then you could do a very simple functional decomposition where you do the compute on one processor and the rendering on the other, see whether that goes faster. I have no idea whether it'll go fast. You'll have some communications to do. Maybe it won't go fast because it's a pretty simple thing. The whole thing is implemented in incredibly inefficient Python, and what you should definitely do is replace it all with NumPy, and if you do that properly, it will go a lot faster. If you do it by looping over the NumPy array in Python, it'll go slower, not faster, but if you do it properly by actually using the Python vector operations, then it'll go faster, and you need to think about how to do that. That's a good exercise too. You should try breaking the grid down in a grid decomposition and doing that communication that I was talking about. That's a really good exercise in learning the blocking and non-blocking stuff and exchanging the boundaries. And I would not worry about updating the display when you first do that. First of all, just check it. And the really important thing to say that I should have been saying right from the start, but you all know this because you're all good professional Python developers, is for God's sake, write some tests. So actually the first thing to do is change. This thing starts with a random game of life. Change it so that you can load an initial state, check what it does in the serial version, check that you think the serial version is right, and then parallelize it and make sure you get the same answer. Because if you parallelize it and make it go fast, but it gives the wrong answer, it's not great. So there's the exercise. So I've taken the fact that there was far too much stuff in this and turned it into a virtue by giving you an exercise. I hope you all appreciate that. Other things we haven't covered, we are very close to the end. I can see you're getting very nervous. But we haven't covered dynamic process management. You can, as I say, instead of using this MPI exec thing that doesn't even work on some people's computers, because, bloody Conda, you can actually just run Python instead. I will be adding to this repo, actually. I'll add a version of the task farm that does dynamic process allocation, because that's what I use. It was too complicated. It's not very complicated, but it was too complicated for today. There's broadcast, which is where you send the same thing to everyone else in a group of processes, which is typically everyone. There's scatter-gather operations, where you send part of it to everyone in a scatter and gather partial results from everyone to combine together, or reduce type operations, which is the same kind of thing, but now you sum them or something on the way in rather than just collecting them all. All of that's left. All of these are documented. As I say, I've got improved, what I regard as improved versions, you might regard as degraded versions, and we've got to the end, if not necessarily through everything, in very nearly the time. It's funny, I had 91 slides and we've taken 91 minutes. And here's all the important stuff. My company, Stochastic Solutions, has a website. I'm also the chief data scientist at Smart Data Foundry, which you don't care about, but it has a website too. The code from today is on GitHub there. You can mail me. I love getting mail. I ignore email, but you could mail me anyway. And, you could link to me on LinkedIn. I'll probably say yes. And I tweet a lot with lots of different handles, and it's a lot of it's shit posting, so just ignore it. And the slides are still available there, and they're available in the repo. And yeah, most importantly, if you're interested in this stuff and want to see more, I'm going to carry on working on these examples, I think. And so I will probably update the repo. If you would like to hear more, do get in touch either by following the repo or mailing me or whatever. And I will probably put a grid decomposition of Game of Life on there, and I'll probably put a version of the task form that you can run with Python rather than MPI exec, both of which I think will be quite useful. And if you find bugs, who found bugs? If you find bugs, I love bugs. Well, I love knowing about bugs. If you find solutions to bugs, that's even better. Pull requests, things like that. Thank you all for your time. I'm sorry it was all a bit random, but hopefully you got something out of that. Go